Okay, it's my pleasure to introduce my dear colleague, Professor Ig-Wan Ju from Princeton University. He's the Robert Porter Patterson Professor of Mechanical and Aerospace Engineering. And you always have to think of words to describe your colleagues. And I could tell you many stories about Professor Ju since he used to have an office next to me, but I won't do that. But I would describe him as a renaissance man of combustion. He's literally done everything from experimental laser diagnostics to numerical methods for chemistry and reactant flows, and really everything in between. So he really has a lot of interest and made some wonderful contributions in different areas. In terms of his background, he got his undergraduate degree from Tsinghua University and his PhD from Tohoku University in Japan, then started as a professor at Tohoku, then went professor at Tsinghua, so kind of went back and forth before ultimately coming to Princeton, where he's gone up through the ranks. And so it's my pleasure to introduce him, and let's welcome Professor Ju.
Okay. Thank you, Michael, for the introduction. And so plasma-assisted combustion, we are going to talk, probably spend about 9 hours. It's in the interface between combustion and the combustion control, and also between combustion and chemistry and probably physics. And it's a more advanced combustion course compared to the basic combustion theory and then chemistry. As we move on, you will see that how important the theory we learned and the chemistry we learned will have to be applied to this process. And just to give brief introduction, that for example, recently I was invited to visit the GE Global and to give a lecture on this for 1 hour. So actually, they have a big problem in the GE new engines because they cannot ignite it when you go to fuel lean. And then they don't know why. The only reason to solve it is you keep increasing the plasma igniter power. But once you increase the plasma power, and you get a lot of overheating of the plasma igniter, and you have to replace it very often. So that's caused a big problem. And for an internal combustion engine, that then in February, there was a international workshop on new combustion concept. There are several people from a company like Nissan and probably Volvo and GM, they come to talk. And they say that to achieve a 50+% of efficiency in internal combustion engine, the important thing to do is to realize lean burn, right? Because more than a third of that the energy is lost due to heat loss to the wall. And you have to reduce the flame temperature in order to reduce that heat loss to improve the efficiency. So the thing to do this, and you have to burn much lean. So once you burn very lean, or you recycle the energy from the EGR, exhaust gas recirculation, and the spark cannot ignite it. And then that is causing a lot of research these days in terms of how to develop a non-equilibrium plasma igniter to realize very lean burn applications. So what I'm trying to talk is try to give you a flavor that from the first of all, from the basics, and then go to the fundamentals application. So let's move forward. So before I talk, I have to appreciate that this project was when I came to Princeton, and I tried to apply for research grant, and then the Air Force encouraged me to think about something differently from traditional combustion. And then this is a project supported by Air Force and later by a multi-university research initiative in collaboration with many people contributed to this project. First, for example, my colleague, Dick Myers, is an expert in laser physics. And then Andrew Stakowski, the research staff at Princeton right now, is a plasma ignition and plasma physics person. And Crystal Locks, and from ICTRO Central Paris, is working on plasma physics. Used to be in Stanford and then moved to ICTRO Central Paris. Igor Adamovich is a plasma physics person and recently moved to laser spectroscopy with a Walter Lampert. And Svetlana Starikovskaya is moved from Russia to Eco Politik. She's a discharge person, expert in that area. And we have a Walter Lampert, laser diagnostics, and a Professor Char, and he's an expert in the area of ionic wind. So, and then we have Anne Borden, and she's a plasma modeling. Rich Yoder is a reaction kinetics, and my collaborator Haixin Wang, and he's working on basically high temperature plasma, mostly using plasma for a space propulsion. And the other people in my lab, Dr. Sang-Hee Wang and Tim Rimbello and and Wen-Tin Song, Joe, they worked in my lab. This is my collaborators from visiting professor Haibao Mu and Qi Chen. And recently there's Mr. Mao, who probably sitting somewhere in this classroom, helped me to do the plasma modeling. So what we try to talk in this 9 hours, hopefully, is that first I try to introduce that what is a plasma discharge. I think that everybody come to this room because you are expert in combustion. Combustion is the flames actually is a weakly ionized plasma. So you have some kind of ion concentration and electrons, but that concentration is very, very low. You could use an electrical field to control it, but it's quite low. And then we try talking about what are the applications, what has been done, and what has been achieved in terms of application. So give you a big picture, what is going on the application side. And then what are the questions there being raised. So after that, we're talking about that what is the effect of plasma on ignition, flame propagation, and the minimum ignition energy from the fundamental of combustion theory. And then we're talking about what is that the plasma can impact. And then number 4, we talk about a electrical field on a combustion. So plasma are 2 different forms. And you can put an electrical field. If the electrical field is below, let's say, the critical threshold, and you only have electrical field. You don't have any kind of a discharge. So that can generate ionic wind. There are a lot of studies in that area. We talk about Joule heating and ionic wind effect on flame dynamics. So the important things of a plasma-assisted combustion is the physics and the kinetics of plasma system. You don't want just to dump heat to heat it. And then you want that the plasma, which has very highly energetic electrons, then can do something chemically to enhance your ignition and the flame stabilization. After that, we talk about the modeling of plasma and the perspective of future research. So let's go to the first one and the introduction of a plasma. So there's a lot of review articles has been put forward in terms of a plasma or plasma-assisted combustion. For example, early days that Alex Friedman wrote a book of gliding arc, basically saying that how to use gliding arc to do a methane reforming or NOx reduction, hydrogen production using a gliding arc. You may not know what is gliding arc. I will tell you later what is gliding arc. And then Laux did a optical diagnostics of a plasma, basically using emission spectroscopy and to tell what is the vibration temperature, what is the rotation temperature by feeding of the spectroscopy. And Starykovskaya wrote Starykovsky, they wrote a review early days about that the global effect about the plasma-assisted combustion. Igor Adamovich and Walter Lampert basically wrote basically how to do that the modeling and then diagnostics and in a plasma-assisted combustion. And then Starek and his expert in quantum ab initio quantum chemistry computation tried to do that the electron impact dissociation reactions rate. And recently that Wen-Ting and me, and we wrote this one more general, talking about the plasma application and then the physics and the chemistry and how do we control it. Any questions so far? It's okay, right? So the next thing I try to talk is that what in 200 years, what we have been doing and what have achieved. So probably 1814, so that the first one is the Brander. They observed that using electrical field, you probably can have some kind of perturbation on flames. That's like 200 years ago. And in 1860s, you see that not I mean, that is about more than 150 years, that the first spark plug was designed and for internal combustion engine. Today, that is probably the similar things, similar things is still used in internal combustion engine because it's very reliable and very cheap, low cost. But as we move for extreme combustion, and the classical design may not be sufficient and to be able to ignite the mixture and to be able to control the combustion. In 1948, Colcott, and who was a professor at Princeton, he did a lot of research of ionic wind, put a DC electric field, and to see how that they affect that the dynamics of the flames and then the soot formations. And he developed a probably more detailed chemistry for ion chemistry, flame ion chemistry, okay, Colcott. And then in 1981, and that is the first that the people developing scramjet engine using high-speed flow. And scramjet engine, as you know, that the flow speed is very fast, and you have less than probably 1 millisecond for the fuel to be injected and be burned. And it's very difficult to ignite and stabilize the flame in probably in a supersonic flow. So the nominal flame speed, basically, that is about a meter per second, about a couple meters per second or a centimeter per second. If you want to stabilize the flame in a scramjet engine, you need probably 1,000 meters per second. So that you need something to ignite it and to stabilize. That's a big challenge. So in 1980s, I'm using the plasma torch. And in the big progress is that probably around 2000, and by Starykovsky and Starykovskaya, and in Moscow, they try to apply this kind of a fast ionization wave. You mean that it generates nanosecond discharge. You generate a propagating ionization wave so that they can discharge fast and in a uniform mixture, so that be able to control volumetric ignition. So, and then probably around a few years ago, that Professor Myers at Princeton and the collaborators tried to say, how do we control the discharge? If I want that discharge to a certain place, how do I control it? He basically using a femtosecond laser and then to shining along the mixture. And then you put two electrodes, and then the discharge will go along the pre-ionization by the laser, because that a discharge try to find the smallest resistance path and to generate ionization. So using a photon to pre-ionize the mixture will help to control where do you want to put discharge. And recently, that by understanding that the chemistry of plasma, and 2 years ago we started using this plasma to generate a cool flame. Normally, that the cool flame is difficult to observe at room temperature, and because the resonance time is too short to initiate that the cool flame chemistry. If you calculate that at let's say at 600 Kelvin, 1 atmosphere pressure, it probably take you about a second for auto ignition of a cool flame, low temperature ignition. But if you have a plasma, they can accelerate the ignition process by 2 orders or 3 orders of magnitude, allow you to be able to observe if the cool flame, as you can see here. So these are I think, give you a highlight about that in 200 years something is changing. So I'm not sure that this is the biggest event in terms of plasma-assisted combustion, but it depends on who you ask. But this is because I'm a combustion person, I think this is one of the things interesting to you. So plasma combustion, you may by names, is that you have to have a plasma, and then you have to have the combustion. So in plasma process, and it is that the plasma physics, you generate two things. You generate electron, right? So electron has a different energy, and from that neutral gas molecules. Electron temperature can be very high. What is the electron temperature here? Inside this fluorescence light bulb. 5,000. What? 12,000. 12,000? 5,000. Okay. Any second guess? So this fluorescence light bulb, and it basically is the electron impact on the fluorescence materials in general emissions. So electron energy is very high. The neutral gas temperature, mercury, for example, and it is very probably 300 Kelvin or 400 Kelvin. But the electron temperature probably about several EV, electron volt, to tens of EV. So 1 EV is 10,000. If you're talking about at least order magnitude higher than what you thought in terms of electron energy. So the energy barrier, for example, for methane, if you have a CH4, right? What is the bond energy of CH4? 100 kilocalorie per mole, right? If we convert to electron energy, it is a few electron volts, right? So if you have electrons, you can break down the bond readily, easily, and with the electrons, instead of heating the entire flow by raising the temperature to break down the bond. So this is at the electric field. And at the same time, they can generate a local heating, they call Joule heating, by electric field. And then they initiate that the electron collisional reactions, because as I said, that the very energetic electrons, they can initiate reaction very fast. For example, in hydrogen ignition, if you heat the hydrogen to a shock tube in let's say 1,000 Kelvin, and you wait for ignition to happen, probably take you about let's say 50 milliseconds, right? So the 50 milliseconds is really limited by what? Limited by the first radicals to be produced, right? Because for hydrogen, the reaction kinetics is very fast. But the mixture is hungry for initial radicals, right? If you have a electron beam or you have a plasma to generate radicals right away, and that process can be dramatically accelerated. This is how that one way that the plasma can control a ignition process. In combustion, that you have a extinction, ignition, of flame speed, and you do want that the plasma can control all of them. And then to understand this, and you have to understand the reaction pathway. That means that my electron impact reactions, which reaction really being perturbed, and that enhance the combustion, right? For a long time, people really don't know. They just see the magics of the plasma can affect the flame until recently, a few years, that they do a detailed spectroscopy measurement, and we try to figure out that what is that the major reaction pathways affect the chemical kinetics. So this is really that, and in addition to that, if you're looking at the simple reaction pathway from a plasma to a combustion enhancement, and you have different ones. The first one, the plasma give you heating, right? If you have put an electric field, a current flow, and you have a resistance, it generates heating. So that heating will enhance combustion through a thermal pathway. It just raises my temperature. So that's easy to understand. The other understand that the plasma, they can generate ionic wind. Plasma has electrons, has ions. If you put the electric field, the ion will be accelerated, and then the electron will be accelerated. But the ion has large cross-section areas. It will collide with the neutral molecule, generate a wind, right? That wind can be a couple of meters per second. It is important because that when the flame stabilization, the flame speed on the base of a burner is only 50 centimeters per second, for example. If you can generate an ionic wind a few meters per second, that can dramatically change your flame stabilization, right? Correct? And also change that mixing between fuel and air so that it reduces soot and control instability. So that's the ionic wind effect. This has been well understood. We'll talk about it a little bit later. Not much really need to be studied. And then the second thing that the plasma, as I said, electrons, they can break down the fuel. For example, you have a jet fuel in dodecane, for example, and they can break down the fuel molecules from large ones to small ones. And then the small ones will have a different diffusivity, right? Will have a different reactivity, and that will change their transport process and some of the chemistry process. But that process is not something we don't understand. We also understand pretty well, but not connecting them to combustion theory. How does combustion theory explain that? Really the thing that the Air Force is funding us for quite a long time is try to understand what are the reaction pathways, which reaction is really dominant in terms of chemistry effect by plasma. For example, the plasma, you can generate ions, you can generate radicals, an intermediate species, you can generate electronic and a vibrational species. How much this reaction will affect the elementary kinetics. That was really something we want to address and in research, and then we finally discussed in this lecture. Applications in plasma that a assisted combustion and a direct motivation was a scramjet engine, and also you can go to afterburners. For example, a military aircraft, they want to fly very high, want to escape, or you want to chase somebody, and you have to turn on the afterburner. Afterburners, basically, they fly very lower pressure, higher altitude. It's very difficult to be ignited because the ignition is very difficult. I'll tell you why. And then you can control mild combustion because mild combustion is different from a regular combustion by what? What is the difference between mild combustion and regular combustion? The difference is the mild combustion is that I don't want to have a flame propagation to control the combustion process. The only thing that I want to dilute the system so that flame cannot propagate, but auto-ignition could happen. It's the ignition-dominated process, right? Ignition-dominated process, plasma is really effective to generate initial radicals and then can accelerate that ignition process. And you can control that a new engine technology, for example, doing low-temperature combustion, cool flames, corona discharge. And you can do fuel reforming these days in Europe. I was invited to go to the plasma chemistry conference to give a talk, and I found that old days, that conference, probably more than half of the presentations was talking about hot plasma, using high temperature plasma torch to make materials or to make a coating or this kind of stuff. But today, more than 70% of that presentation is non-equilibrium plasma to do something like a fuel reforming, CO2 reforming, particularly from Europe and Japan. They are cared about that the CO2 emissions. They wanted to use in plasma to do something, particularly with renewable energy. You have a lot of wind blow, you have a lot of sunshine, you cannot use it sometimes. How can we use the plasma to make a good use of it? And recently we also funded by ExxonMobil and to do this type of research. And then you have to control emissions by reducing that combustion temperature so that you can reduce emissions. A lot of things in combustion area, but there are more things far beyond combustion area. For example, you can do a material synthesis. And this year, Air Force called a multi-university research initiative saying that how can we make new materials by using plasma. Plasma, pretty much you can dissociate all different kind of molecules. You can put it together, a new material they never seen it before by nature, right? So you can make a plasma medicine, for example, using plasma to sterilization and to kill bacteria. Probably some people say, how do we kill cancer cells? There are people doing this type of research. Plasma cleaning, for example, semiconducting companies, cleaning the wafer surface is very important. The people using plasmas to clean the surface. And then nowadays, there's water treatment using ozone or the plasma discharge to treat that the wastewater is also an important area. So I think that my interest to get into this area is because that it's not only that because I like plasma, it's mostly like that the plasma can range from low temperature to high temperature, from combustion to different areas. That is much more broader application, and then enrich the physics and chemistry phenomenon. So a plasma, so let's start this class. We're talking about what is plasma. And then most of you probably you know it very well, but some of you may not. So plasma is that it's a force of matter, right? It's basically that it's a mixture of neutral molecules and ions and electrons. So it says that it's quasi-neutral, a charged mixture, and which contains an electrons and ions, and they can separately free. A separately free does not mean that you can move, electron and ion can move freely, independently. That's not true, because you are neutrally, electrically neutral, so that when the ion move and they generate electrical field, they will affect electrons. They have to move together, right? So this is that so plasma basically has many definitions. For example, depending on the frequency, the first one, I have a DC plasma, then a direct current plasma, right? I have AC plasma, is like an alternating current, right? I have a radio frequency plasma, That means that my frequency probably is at 100 kilohertz to 100 megahertz. That is a radio frequency plasma. And I have a microwave plasma. It basically is at a few gigahertz to a tenth of a gigahertz of a plasma. This is a frequency. I have another recently that people doing pulsed is a plasma. I have a DC, but I'm pulsed. 1 nanometer, 1 nanosecond, 10 nanosecond. So these are all different kind of a plasma developed in terms of frequency. And also you call that the plasma in terms of temperature. For example, we call a thermal plasma. That means that it's very hot. By means thermal, that means that the neutral molecules, that the gas temperature is ranging from 2,000 probably to 20,000 or even higher, depending on how much energy you put it in, right? And in that case, that the transitional temperature of molecules and rotation, vibration, and electron temperature all almost the same. Everything has a Boltzmann distribution, not exactly the same, but by average, they're almost the same. So every mode, energy modes, they are in equilibrium due to intense collisional energy transfer, right? So this we call a thermal plasma. For example, arc, lightning, and these are close, and spark plug. And then we call another category called a non-thermal. That means that these temperatures, they don't equal to each other. There's not enough time for them to collide, to equilibrate. Either that the pulse is very short, or the mixture is so dilute. There's no way you can collide frequently. And how many collisions you can change vibrational energy, for example? For the rotational, yeah, thousands. For rotational, just one collision will be probably can be able to transfer. But a vibrational will take about 1,000 collisions. So that we, for example, particularly that if in low pressure and you don't have enough collisions, and then for example, short pulses like a microwave corona and a micro discharge, they don't have a time for the energy transfer. So that you may have a equilibrium between transitional and rotational, but you don't have a between rotational and vibrational and electronic excitations. So these are category of temperature. And also you call it discharge process. The discharge can be electric field, just like DC or AC. It could be a streamer. You generate a streamer propagating in the mixture. It could be something like a glow discharge. It could be arc or corona. This all depends on that the type of discharge in the mixture. And then you can be for example, dielectric barrier discharge, gliding arc, and micro, everything. We call different names by applications, by that the design of the plasma. But once you know this thing, the category, and people tell you one thing, and then you know, whether that what type of plasma is. So the important thing is that one of the important parameters is that plasma frequency. So why do we worry about plasma frequency? Plasma, you have ion, you have electrons. And if you put an electric field, and that ions will move, and electrons will move, right? So if the frequency is very low, the ions will follow whatever electric field you put it there. But if your electric field is very, very fast, like a microwave, and the electrons, the ions, they cannot catch it up, right? They cannot catch up the frequency change about the microwave. And then the energy you put it there will be either directly transmitted or directly reflected, because they cannot respond to the frequency and you have. So what is the fundamental frequency of plasma? So this is a very simple mechanics. For example, if you have a quasi-neutral plasma like that, positive and negative. So let's say you put the electric field, E, to perturb that the charges. Let's say that the electric field is this direction and the electrons shifted to that direction. So you can calculate that the total charge number equal to the charge per electrons times the volume times the number density of that the electron number density. And then the electrical field basically saying that, okay, I have an electrical field is that the total charge and net charge divided by that the permittivity and then surface area. So you can calculate this guy from Q to generate this is that the electric field. And the force acting on the particle is that the charge times the amount of electric field is QE. So it's like that. This is the force. So this will be the force acting on individual particles, right? So you can write down a simple Newton equation. So Newton equation basically said F equal to ma. Here's my F. Here's my m electrons, and this is the change. So this is like a oscillating spring equation, right? Correct? This is like a friction. This is like that accelerated force. So you can write down that the frequency is just the square root of this guy. And you can write down, you get 9,000 square root of number density of electrons. So you give you estimate if an electron number density is 10 to the 9th, 10 to the 9th per cubic centimeters is really low, right? So you put this number into it, and you can calculate that the frequency is about 300 megahertz. 300 megahertz is the plasma frequency, right? And if frequency is higher than that, they cannot respond to you. If below that, they can always respond to you, right? So that is that the electron, the plasma frequency is very critical to the electromagnetic wave propagation. So if you have a frequency, the electric field is smaller than that plasma frequency, and then the electrons in the plasma always respond to you, and then they will build a internal electric field and try to reflect the electromagnetic wave. But if that the plasma frequency is larger than if the electric field frequency is larger than plasma frequency, and the plasma cannot respond fastly to change that the charges. So therefore, the electric field will be transmitted through the plasma without any reflection. So therefore, there is a critical plasma number density, which is that here, at which that the frequency will be equal to the plasma frequency. For example, that for microwave frequency, that is 2.45 gigahertz, and then let's say that if the electron density is like that, you generated that the plasma frequency is 2.7 gigahertz. It's slightly above that the incident microwave frequency. So this means that the microwave will not penetrate the inside of the plasma, and then everything will be reflected or transmitted depending on the frequency. So this is the very important problem. This is why that microwave is good to be used in controlled combustion at high pressure. Because that if that the frequency is so high, higher than that, and then they either be transmitted, not to be really engaged with that heating, avoiding overheating. And then, so if you're looking at the other one is the mean free path, and everyone you learn that combustion and the statistical mechanics, and you know what is the mean free path. And why do we need to talk about here? Here the mean free path is that we talk about the electron collisional mean free path. It's slightly different from the neutral molecules, because that's governing that the energy transfer between electrons and neutral molecules. So if you have a mean velocity and in particles, the u, and you have relative velocity basically be calculated between the two different particles, that is probably square root 2 of u, and you probably learn from statistical mechanics because there's the relative velocity. And then you can say my mean velocity is that my velocity times a distribution function, and this is at the temperature. So this is the mean velocity of molecules traveling. So if you have a particle have a diameter d, and then you have the collision numbers per unit time will be that the cross-section areas times the velocity and times the number. This is the volume times the number density, how many collisions will be. The mean free path is very simple. Is that the distance you traveled per unit time and divided by the number of collisions and per unit time. You generated this one. So everybody knows this is the basics of kinetic theory, classical kinetic theory in terms of mean free path. So if you put the number in at 300 Kelvin, 1 atmosphere pressure, and the molecular diameter for air is like 3.5 angstrom, and you calculate that the mean free path is about less than 0.1 micrometer. It's very, very small in terms of mean free path. If you're talking about electrons the electrons are much smaller than the neutral gas, and much faster too. So the relative velocity of a electrons is that you generate electron-neutral collisions will be the electron velocity normalized by cross-section areas. This cross-section divided by 4 is because that the electron cross-section area is very small. So you generated this kind of a collisional. The mean free path for electrons is higher than the mean free path for the neutral gas. So the collisional frequency can calculate the same way as you do for the neutral gas. So this is that it gives you estimate what is that the mean free path, and how does the mean free path play any role in terms of plasma. So that's the question. So next thing that is that the Debye sheeting effect and then plasma shifts. So if you put a 2 electrode and with a DC discharge, DC voltage, and the voltage will not linearly decreasing between the electrode. They will drop significantly between near the surface of the electrode. That we call sheath effect. So what does it mean by sheath effect? Sheath effect is that is something that if, let's say I have a electrically neutral plasma mixture with ion and electrons, I suddenly bring in a positive discharge or bring in an electrode there. And then once you bring an additional discharge or electrode there, the ions and electrons will redistribute, try to respond, right? Correct? So once you respond, for example, if I have in this kind of a neutral plasma, if I put a charge object, a perturbing charge, is a positive Q here, and then of course the electrons try to move to be attracted to the Q, and the ions will be repelled, right? You generate disturbing in this radius. Outside of this radius, and everything business as usual. So this distance we call a Debye length, lambda d. So within this radius, and then the charge is perturbed, and outside, all this effect is shielded. Even you put the charge there, there's nothing affected outside the radius. I give you a visual example. Let's say this is at the gliding arc. This is at the anode, for this is the cathode. You can generate an arc discharge. You can see at the anode, you can see very bright spot there. That is the sheath of anode. And here that you can cathode, you can see the bright spot there. That is the sheath of cathode. And what it means by sheath of cathode, you can see there in the middle between here, everything is neutral. One ions, one electron, positive electron, pretty much is neutral. But near the electrode, that the electrons move much faster than the ions, right? And then you generate this kind of a net charge of the positive ions. So this is the electrode, and the length scale, if you put the electrode and in a plasma, and you have this kind of a length scale called sheath, where that the voltage drop a lot during the sheath. Okay, this we call a sheath. So the Debye length is relevant to that the length scale of the sheath of the electrode. So when you do a plasma-assisted combustion, you try to quantify what is that the field strength, and don't forget that the sheath may play a big role in affecting the voltage distribution in the plasma. Okay, how large is the Debye length? Well, it could be close to what? Collisional mean free path, could be. But you have to start from that the Debye length. If you look in the Maxwell equation, that the divergence of electric field is proportional to the net charge and divided by the permittivity of the plasma. So, and then for a steady state problem, let's say I have a DC discharge, and I have electric field just equal to my gradient to potential. So therefore, you can make a divergence of this one, left-hand side, and then you can write down that the the second derivative of phi just equal to this one. So you make a divergence of this one and replace this guy. You can write down, this is the Princeton equation. You can solve it, right? And before you solve it, we can normalize it. Normalize what? By the length scale, right? The second derivative in space always give you a characteristic length scale, right? Just like diffusion, always give you diffusion length scale, right? So a second derivative gives me a length scale. So if I normalize this equation and then multiply by phi by E and divide by KB, a Boltzmann constant, and then at electron temperature, I can normalize this one by using this equation. Here is the length scale, and lambda d is the balance scale. So here is the balance scale and can be derived through this normalization of these equations. If we put a number there, let's say if my electron temperature is at 1,000 Kelvin, and my number density is about 10 to the 13, which is about 1 ppm. And then we have the balance scale will be less than 1 micron. You see, they're very small. So you can, if you're talking about plasma, at this condition, you can imagine that the plasma pretty much is neutral everywhere, except a submicron length scale near the electrode, right? So that's why people always make assumption that plasma is neutral. It's neutral because the balance is so small at these conditions. But it cannot be small when the pressure, if the pressure is really, really low, then you have a problem, right? Then it cannot be very small. So, so that is we say plasma is almost quasi-neutral everywhere except the schist, and the schist is very small. It's sub-micrometer in most of the conditions. So what if that you don't have a steady state and you have unsteady plasma discharge? You have to using a Maxwell equation, and then to write down this one at the electrical field and the magnetic field coupling, and then using this Maxwell equation. And here that the J is that the current. The current is formed due to what? Due to the mobility of ions and due to the mobility of electrons. So therefore that you have two components, is the motion of ions and the motion of electrons. So if you redefine, we define that my ion velocity is equal to the mean velocity adding a diffusion velocity. Just the same thing you do in combustion. My velocity of species I equal to the mean velocity plus the diffusion velocity. We can write down the ion and electrons like that. You substitute this into this equation, you can get that the current equal to that the charge, mobility, and the diffusion mobility. So you can define that the diffusion mobility is basically that equal to the diffusion times that if you flip this one back, you can write down equal to the electron mobility and then diffusion mobility. Same for the ions and electrons. So the question to ask is here, the electrons they diffuse and the ions they diffuse, but you cannot diffuse too far away because I am going to attract you if you move away, right? So therefore, they have to be interacted together. So the question is, how do I define the diffusivity in a plasma, right? It cannot be defined independently. So from Einstein relation, we can derive that the electron mobility and diffusivity in terms of a temperature, electron temperature, and the neutral temperature. But this process has to be coupled in the plasma. So they cannot diffuse independently. So we need to define what is that the global diffusivity for electrons and ions. So if we write down that the diffusion process equal to electron mobility and then the concentration gradient. And then in steady state case, and then because plasma is neutral, right? Neutral means that my flux has to be cancel each other. So therefore that the flux of ion and electrons has to be equal. If you equate these two equations, and then you get that electric field combined together, you will say my electric field is equal to the concentration gradient of the electrons and multiplied by the difference of diffusivity and divided by the mobility. So this is that the electric field and the electron ions they create try to balance the external electric field. I have external electric field E, but internally I have ions and electrons diffuse. I generate internal electric field to counter you, and then become a steady state, no motion, right? So this is that the diffusivity. So therefore, you substitute this E back to this equation, you can get that the flux of electrons and ions, and in the form of that concentration gradient multiplied by a D. This D is combination of these two we call ambipolar diffusion. So when you calculate the plasma combustion, and you have to using the ambipolar diffusivity to calculate that the ions and the electrons, because they interact with each other. Okay? So we talked a lot about frequency. We talked about the critical length scale, about the valence. We talked about the diffusivity. So what is the next? The next thing you both should be, what is the critical value for ionization to happen, right? So in a plasma, the plasma starts from an electric field. That electric field causing an ionization of a molecule generate ion and electron. So generate ion and electric field generated ion and electron. So this ion and the electron will be accelerated in an electric field and gain energy. And that energy will collide with a second molecule and create new ions and new electrons, and maybe causing that a vibrational excitation of the molecule as well. So this is that the energy transfer from electrons to ionization and the electronic excitation and then vibrational excitation. This electronic excitation could generate a light emission, photon ionization, emit that the light like here. And it could be generate a new electrons, and at the same time that the vibrational excitation or electronic excitation of molecules enhance the reactivity of fuel. For example, if oxygen is electronically excited, H plus O2 equal to O and OH reaction is the number one important reaction, right? Let's say I'm electronically excited that oxygen molecule. My oxygen molecule is electronically excited. The energy barrier for H plus O2 reaction will be dramatically reduced, right? So that changes the reaction pathway, will chemically active. And this energy will be transferred to rotation and transition through collision process. If the collision is not enough, then the process will be a higher energy of vibration and electrons. You will become non-equilibrium. If the collision is fast enough, and then you establish a equilibrium plasma. That's a thermal plasma, right? So this is that the process that how from electron energy and go to non-equilibrium excitation, make it more new electrons and make it chemically active, and then in the end they transfer to heat. So these are physical process of energy transfer. So the question is that in plasma-assisted combustion, what is the time scale of this? If this time scale is too slow, forget about it. You cannot control combustion. If this time scale is much faster than the combustion process, then we'll say that plasma can play a potential role in governing that the combustion control. Is that right? Okay. So next thing, I try to show you a number that using a laser absorption, not laser absorption. This is that the measurement by a time resolved and spatially resolved measurement of nitrogen vibrational temperature in a nitrogen plasma. So you have a microplasma is a needle to needle plasma. So this is measured by a Professor Walter Lampert at Ohio State using a combination of a femtosecond laser and a picosecond laser. the excited that the vibrational state, you can see the red one is that the this is the transitional energy. You can see that the vibrational excitation of nitrogen goes on, and then continue to increase and then decrease. This increase is because of what? The first peak of vibrational excitation is because of what? Electron impact, right? Electron direct impact, because electrons so fast impact, excite the molecule. And then this nitrogen is continue to be excited by collisional energy transfer through higher energy of excited molecules electronically or higher a vibrationally excited molecule, and it can second peak and then decay. If you look at here, this is temperature. This temperature arises at the same time as the vibrational excitation. This means that it's electron impact heating process, right? We call fast heating, remember. This is fast heating. And then here, as the vibrational energy decrease, temperature decrease, and I still have some rise of static energy. This is the energy transfer from vibrational energy to transitional energy, correct? So this we call slow heating. So in a plasma process, in addition to that, the electronic effect and the chemical effect of energetic molecules, you still have heating. This heating has two stages: is fast heating and slow heating. If you look at the time scale, that this 10 to the minus 9, within 100 of a nanosecond, the fast heating complete, right, at 1 atmosphere pressure. And the collision frequency in 1 atmosphere pressure is what? 10 to the 9th, right? So it happens at 100 collisions that generate. And then here is that the 10 to the minus 4 using the vibrational relaxation takes about milliseconds to happen. Take quite long in terms of vibrational energy transfer to transitional energy. So this is that another computation and measurement, and basically showing you that this is that I think that the blue ones probably is probably electric field, and then nitrogen excitation. And this one is that vibrational, this one static. You can see that during the peak of nitrogen electronic excitation, and then you can see the decay and the temperature rise. So this temperature rise clearly is due to electronic excitation process, energy transfer. And the second one is that the rise of temperature is due to the vibrational relaxation. So electronic process and the vibrational relaxation, these are the two major processes in terms of heating. Okay? So two stages of heating process, which is plasma. So then we're talking about it, okay, in addition to heating, what is that the chemistry effect of plasma? If you're looking at the electrodes, and I have electron collide with a molecule, and ionize it and generate the electrons. And people doing a, what is that called? Molecular electron impact molecular beam spectroscopy, MBMS, right? How many people do that? No one in this lab? Okay. You using electrons to heat the molecule and ionize it and then accelerate it and then measure the concentration. So this is that basically an electron impact ionization. So ionization has a different process in plasma. Plasma has electron and also has photons, all right? Also has heat. All three processes can dissociate a molecule, generate electrons, right? So by photons, you have one photon, and heat oxygen, it generates ionization. By electrons, you can also, and by a thermal collision, you can also ionize. These are three processes to ionize that the molecule to generate a second electron for electrons to go to chain branching reactions, accelerate, right? One electron generates two, for example. It can also have a recombination. When you have a lot of electrons, the electron collide with a molecule, they attach to a molecule, and the electron number density will decrease. So this we call a recombination and attachment. Electron impact and attach to it, electron recombination, electron and ion recombination, they dissociate this oxygen through a ground state and the excited state. So these are the process of recombination process. And then, for example, the plasma temperature, normally that we measure the plasma temperature is that, let's say, 1 electron volt. Let's say electrons accelerated by 1 volt. Then you gain energy, 1 electron volt. It's easy, right? If there's no collision. Once they collide, of course, you will lose energy if you don't. So 1 electron volt is equivalent to 11,000 Kelvin. So this kind of plasma there, they have tens of electron volts. Okay? So have very high energy to break down that the mercury atoms there to ionize it and generate electrons, right? So, so this electron energy is normally in a plasma is measured, is influenced by electric field strength, E, right? E, electric field strength. And then depending on how many collisions, that is governed by number density, right? So the E over N is that the electrical field in a plasma governing that how high the electron energy will be for a given mixture, right? If the mixture changes, helium and nitrogen, of course, they're different. But for helium and nitrogen, if you give me a E over N, I can tell you what is the mean electron temperature. Because the E is how much energy you gain. The N is how much energy you lose due to collision. Right? So E over N is a very important parameter of plasma. So everybody, when you present a plasma combustion, the expert always asks you, what is your E over N? You said, I have 1 tonsant. What does it mean, 1 tonsant? Is that the E over N becomes 10 to minus 21 voltage per square meter is 1 tonsant. What is the tonsant? How many tonsant required to break down the air? Do you know? You know that 1 millimeter in air, you need about 3 kilovolt to break down for 1 millimeter. That equivalent to about 100 tonsant, right? A few hundred tonsant to break it down. Okay, this is a measure. So in terms of equilibrium and non-equilibrium, everybody knows that we have a Boltzmann difference. We're talking about Stephen Cliffstein will give you a theory. The theory basically that all excited mode, rotational, vibrational, and they are in Boltzmann distribution or Maxwell-Boltzmann distribution. But what I'm going to tell you here, in plasma, particularly non-thermal plasma, you don't have a Maxwell-Boltzmann distribution because it's highly non-equilibrium. So that if I give you E over N, how do I know my temperature? The electron temperature distribution has to be solved. Solved by what? By Boltzmann equation. You have a collisional relaxation term here. So this is that how to people to solve that the electron energy in a plasma, synthetic combustion. So a few examples. For example, lightning is that arc. 1 atom of pressure is very hot, and then enough collision to equilibrate this probably close. If you're talking to a professor at PPPL, they might disagree. But to me, I think that first order, they're right. And then if you see that the arc, if you blew the arc, if you form the arc, if you blew the arc with the convective heat transfer, what will happen? I have a lot of heat losses, right, from the arc. If you have a lot of heat loss, the electron number density will decrease. If the electron number density decreases, the current will decrease, and then the voltage will increase. If the voltage increases, then my electron energy is going to gain. If they move here, my gliding arc, then my electron energy is going to gain, become larger than a neutral molecule. And if I have a very short pulsed plasma, there's no time for equilibrium to establish. At that time, like a coronal discharge, I have electron temperature much larger than vibrational, much larger than the neutral gas. So this is a typical example of from thermal plasma to non-equilibrium to far non-equilibrium plasma, right, in a application. I think probably we take a break here, and then 15 minutes we'll come back. The plasma is a very complicated process, and to me it took me years to understand what it is, really, particularly the relation between that. So I think that you may have a question, and you may don't understand, but I think that in the future, when people are talking about this, and you understand what is the physics, that's the important thing, okay? If you have any question, and during break time, you can talk to me. So take a break first. Question?
Yeah, so one of the things you showed was a gliding arc.
Yeah.
I was wanting to have an understanding of why that happens. So you have a kind of a curve between the two electrodes.
So a gliding arc, the merit of gliding arc is that it sits in between a equilibrium hot plasma and then non-equilibrium cold plasma. It has the merit that it has higher temperature, the temperature around 2000 Kelvin, which is good enough to ignite the mixture in combustion. And it has a higher number density compared to a non-equilibrium plasma. They have a benefit of those. And let's say you have something like this. Okay, you generate an arc between it. If you convectively blow this arc, the arc will have to be strained, right? And then the arc becomes longer and longer and longer. I mean, getting cooler and cooler and cooler until it dies. So that is we call gliding arc. It has the non-thermal effect but a higher electron number density. So it is very effective in terms of flame stabilization. Okay. Well, we'll come back and probably in 15 minutes.